Let me ask you a simple question. A child's question, really? If you had a rocket ship with one engine, you could go fast. If you strapped on a second engine, you'd go faster. A third engine, faster still. So what if you kept adding engines? 10 engines. 100 engines. 1,000 rocket engines all firing at once. Could you eventually go faster than light? Your instinct says yes. Of course, yes. More engines, more speed. It's obvious. It's common sense. Add enough power, break any speed limit. That's how speed works, right? You can always go a little faster. There's no invisible wall in space that stops you. Except there is. And that wall is light itself. 186,000 miles per second. That's not just the speed of light. That's the speed limit of the universe. Nothing can go faster. Not rockets. Not particles. Not information. Not you. No matter how many engines you strap on, no matter how much energy you pour into your spaceship, you will never, ever reach the speed of light. Let alone beat it. Why? What makes light so special? What invisible law of physics reaches out and stops you right before you hit that magic number? The answer is going to sound crazy. The answer is going to break your brain. But it came from Albert Einstein, and it's been tested millions of times, and every single test confirms it's true. The reason you can't go faster than light is because the faster you go, the heavier you become. I know how that sounds. I know what you're thinking. That's ridiculous. My weight doesn't change when I run. My car doesn't get heavier when I drive faster. And you're right. At normal speeds, the effect is so tiny you'd never notice it. But it's there. It's always there. And as you approach the speed of light, it becomes impossible to ignore. Let's start where Einstein started. With a thought experiment. Imagine you're floating in space. You're in a spaceship, engines off, just drifting. Now you turn on one rocket engine. It pushes you. You accelerate. You start moving faster. Simple physics. Force creates acceleration. Now you turn on a second engine. Same size, same power. You'd expect to accelerate twice as fast, right? And you do. Almost. But not quite. The closer you get to the speed of light, the less each engine helps. It's as if your spaceship is getting harder to push. Like you're gaining weight. And you are. You're gaining mass. Not pounds of physical material. You're not growing bigger. But the energy of your motion, the kinetic energy, is adding to your mass. Einstein discovered that mass and energy are the same thing. E equals mc squared. Energy is mass. They're interchangeable. When you're sitting still, you have rest mass. That's your normal mass. But the moment you start moving, you gain kinetic energy. And that energy has mass. At normal speeds, a car driving down the highway, the added mass is so tiny you could never measure it. But as you approach the speed of light, the kinetic energy becomes enormous. The mass becomes enormous. Let me give you numbers. If you're traveling at 90% the speed of light, your mass has roughly doubled. You're twice as heavy as you were at rest. If you reach 99% the speed of light, your mass is now 7 times your rest mass. At 99.9%, it's 22 times. At 99.99%, it's 70 times. Do you see the pattern? The closer you get to light speed, the heavier you become. And the heavier you are, the more energy you need to go faster. It's a vicious cycle. You add more engines. You pour in more energy. That energy makes you heavier. Being heavier makes you harder to accelerate. You need even more energy, which makes you even heavier. At exactly the speed of light, your mass would be infinite. It would take infinite energy to get you there. and infinite energy doesn't exist. You can fire 1,000,000,000,000 rocket engines. You can harness the power of 1,000 stars. It doesn't matter. You will get closer and closer to light speed, but you will never reach it. The universe won't let you. Now you're thinking, okay, but what about light itself? Light travels at light speed. How does light do it? Brilliant question. Einstein asked the same thing when he was 16 years old. He imagined chasing after a beam of light. What would you see if you could catch up to light and move alongside it? The answer led him to special relativity. Light can travel at light speed because light has no mass. 0. Photons, the particles of light, have no rest mass at all. That's the loophole. The speed limit only applies to things with mass. If you have mass, you can never reach light speed. If you have no mass, you must travel at light speed. You can't go slower. Light doesn't have a choice. This is deeply weird. Light is born moving at maximum speed. It never accelerates. It never slows down in vacuum. From the moment a photon is created until the moment it's absorbed, it travels at exactly 186,000 miles per second. Not 185,000. Not 187,000. Exactly 186,000. Every photon. Everywhere. Always. But here's where curiosity pulls us deeper. Why is the speed limit exactly that number? Why 186,000 miles per second? Why not 1,000,000? Why not 1,000,000,000? What's special about that particular speed? Nothing. The number is arbitrary. It's an accident of how we define miles and seconds. But the fact that there is a limit, that there is a maximum speed for cause and effect in the universe, that's fundamental. That's built into the structure of reality itself. Think of it like this. You're playing a video game. The characters can move around the screen, but there's a maximum frame rate. The game processes information at, say, 60 frames per second. No matter how fast the character tries to move, they can't go faster than 1 pixel per frame. That's the speed limit of that digital universe. It's baked into the code. Our universe has a frame rate too. It's the speed of light. That's the maximum speed at which cause and effect can propagate. It's the speed at which information moves through space. Nothing can happen faster than that because the universe itself updates at that rate. Let's make this concrete. Imagine you're standing on Earth and your friend is on Mars. Mars is, let's say, 12 light minutes away. That means light takes 12 minutes to travel from Earth to Mars. You shine a laser pointer at Mars. When does your friend see the light? 12 minutes later. Not instantly. Not in 1 minute. 12 minutes. No matter how powerful your laser, no matter how much energy you use, the light takes 12 minutes to get there. Now imagine you want to send a message faster. You can't use light. That takes 12 minutes. So you try something else. You get clever. You take a really, really long stick. A stick that reaches from Earth to Mars. You push one end of the stick. Your friend on Mars feels the other end move instantly, right? You've beaten light. Wrong. When you push one end of a stick, you're not moving the whole stick at once. You're creating a compression wave that travels through the material. Atoms push against atoms, pushing against atoms, all the way down the length of the stick. And that wave travels at the speed of sound in that material, which is much, much slower than light. Your friend on Mars wouldn't feel the push for hours. Maybe days, depending on the material. Okay, you say. What if I get a perfectly rigid stick? A stick that doesn't compress at all? No such thing. Perfectly rigid materials are impossible. They would require information to travel instantaneously through the material, which would require faster-than-light communication. Which is exactly what we're saying is impossible. The speed of light isn't just about light. It's about causality itself. Every attempt to beat light runs into the same problem. You try to use gravity. Gravity waves travel at the speed of light. You try to use quantum entanglement. Information still can't travel faster than light. You try to use wormholes. Even if they exist, you can't send information through them faster than light would travel through normal space. The universe has closed every loophole. Let's go back to your rocket ship with 1,000 engines. You fire them up. You accelerate. You're going faster and faster. You check your speedometer. 50% of light speed. Then 60%. Then 70%. You're doing great. You add more engines. More fuel. More energy. You hit 90% of light speed. But now something strange happens. You fire the engines even harder, but your speed barely increases. You're pouring in enormous amounts of energy, but you're only gaining tiny fractions of a percent. You hit 99% of light speed. The engines are screaming. You're burning fuel at an incredible rate. And you're barely moving faster. From your perspective inside the ship, everything feels normal. Your engines are firing. You're accelerating. But from the perspective of someone watching you from Earth, you're getting heavier and heavier. The energy you're pumping into the engines is mostly going into making you more massive, not making you faster. At 99.9% of light speed, you're now 22 times heavier than when you started. To go from 99.9% to 99.99%, you need to multiply your energy again. And again. Each tiny step closer to light speed requires exponentially more energy. It's like climbing a mountain that gets infinitely steep as you approach the summit. You can climb forever and never reach the top. This is why particle accelerators are so big. Scientists smash particles together at 99.9999% the speed of light. To get particles to those speeds, they need machines miles long that consume massive amounts of electricity. And even with all that power, they can't quite reach light speed. They get close. Incredibly close. But never there. Now here's where Einstein's curiosity leads to something beautiful. If nothing can go faster than light, then light speed isn't just a speed limit. It's a cosmic constant that connects space and time. The reason you can't go faster than light is the same reason that time slows down when you move fast. It's the same reason that space contracts in the direction of motion. It's all the same phenomenon. When you move fast, time slows down for you. Not in your perception. To you, time feels normal. But compared to someone standing still, your clock ticks slower. At 90% of light speed, your clock runs at about half speed. At 99% of light speed, it's running at 1/7 speed. At exactly light speed, time would stop completely. This is why light itself doesn't experience time. A photon is born and absorbed in the same instant from its own perspective. For a photon, its entire journey, whether it's a millimeter or a billion light years, takes 0 time. The photon doesn't experience anything. It exists in a timeless state. So can you beat light? No. Can anything beat light? No. But here's a curious twist. Space itself can expand faster than light. The universe is expanding. Distant galaxies are moving away from us. And some galaxies are so far away that the space between us and them is expanding faster than light can travel across it. We will never see those galaxies because their light will never reach us. Not because the light is slow, but because space itself is stretching faster than light can cross it. This doesn't violate relativity. Nothing is moving through space faster than light. But space itself can grow at any rate. It's not moving. It's expanding. And there's no speed limit on the expansion of space itself. There's another curious loophole. While nothing can go faster than light in vacuum, light can be slowed down in materials. Light travels slower in water than in air, slower in glass than in water. And in certain exotic materials, light can be slowed to walking speed, or even stopped completely. If light is moving slow enough through a material, particles moving through that same material can move faster than the light in that material. When this happens, you get a phenomenon called Cherenkov radiation. It's like a sonic boom, but for light. A blue glow. You can see it in nuclear reactors. Particles moving faster than light in water, creating a shock wave of blue light. But even this isn't beating light. You're only going faster than light in that specific material. If you measured your speed in vacuum, you'd still be slower than light's speed in vacuum. The universal speed limit still holds. So here's the final answer. You cannot beat light. Not with 1,000 rocket engines. Not with infinite energy. Not by being clever with sticks or quantum mechanics. The speed of light is the speed of causality. It's the maximum rate at which anything can happen in the universe. It's not a suggestion. It's not a challenge. It's the fundamental structure of space-time. And yet, despite this absolute cosmic speed limit, light itself seems almost casual about it. Every photon, from every star, from every flashlight, from the screen you're reading this on, travels at exactly that speed. Effortlessly. Eternally. Light doesn't try to go fast. Light doesn't accelerate. Light simply is fast. Maximum fast. The fastest fast there is. Einstein saw this when he was 16 and wondered what it would be like to ride alongside a light beam. That curiosity led him to realize that time is relative, that space and time are connected, that mass and energy are the same thing, and that the universe has a speed limit that cannot be broken. The question, can you beat light? Sounds like a challenge. Like something to overcome. But it's not. It's a fundamental truth about the universe you live in. The speed of light is the speed at which reality operates. You are made of atoms held together by forces that propagate at light speed. Your thoughts are electrical signals in your brain that can't exceed light speed. You are a creature of light speed. You exist at light speed. So no, you cannot beat light. But light isn't your enemy. Light is the fabric of causality itself. And understanding why you can't beat it, that's how you begin to understand how the universe actually works. That's the real victory.